Hello everybody, I hope you're all doing well. We're going to be solving one more problem on static friction. This is the concept of tipping motion versus sliding motion as I have written out there. Okay, in this problem we have a box which is labeled as capital B, and then you have a person. This person is trying to push the box. The mass of the box is given to us as 50 kilograms. Okay, I'm just going to put a tick mark down here. Mass of the box is given to us. The mass of the person is 75 kilograms. Dimensions for the person is not given to us. Okay, and then we are also told that acceleration due to gravity is 10 meters per second square. Okay, then I'm given the coefficient of static friction between the box and the ground. Okay, so coefficient of static friction between the box and the ground. So mu Bg is between the box and the ground is 0.3. Box and the ground. And the other coefficient of friction is between the person and the ground, which is 0.4. Okay, this is between person and the ground. All right. So what are the things that we need to find here? What are the things that we need to find are the following. I guess only one thing. Find the minimum force which the person should push on the box so that the motion impends. Okay, so find the minimum force applied by the person on the box such that motion impends. Okay, so this is what we need to find. All right, then we will assume that the force applied by the person, and you can further assume. Okay, so assume person pushes on the box horizontally. Pushes on the box horizontally. Okay, so this is what we can also assume in this particular problem, and some kind of nomenclature, right, before we start the solution. Okay, so solution first, and before I start doing any of the calculations and so on, here are the things that I'm going to be writing down. So I'm going to have F mu Bg, and then I'm going to have F mu Pg. Okay, this is the friction force between the box B and the ground G, and this is the friction force between the person P and the ground G. Okay, and then likewise I have N BG, NPG. Okay, normal force between the box and the ground, and likewise normal force between the person and the ground. All right, so this is the nomenclature that we have, and then I can also find out the weight of the person. Okay, so weight of the person is mass of the person times acceleration due to gravity. Mass of the person is given to me as 75 kilograms. 75 times 10, so that's going to be 750 newtons. And then the weight of the box is mass of the box times acceleration due to gravity. Mass of the box was 50, which means that this is going to be 500 newtons. All right, I just want to scoot this down a little bit so that this is important information that we are actually calculating based on what is given to us in the problem. Okay, the mass of the block is given to us, and the mass of the person is also given to us. All right, so with all of this, let us get going on the problem. One more thing I want to point out is I want to have the point C. Okay, so I'm just going to draw a point here. Okay, so that I'm going to call as the point C. Okay, so C is the point of contact on the ground, okay, between the box. Okay, it's a corner point. Okay, so C, let me also make a quick note of that. Okay, so point C is a corner point or contact point between end of the box and the ground. Point of contact between B and G. Okay, just for reference, as you can see here. Okay, so this is this point C that I'm talking about. All right, and G is the ground anyways. All right, so what are the cases of impending motion? Okay, so cases of impending motion. In this problem, there are actually, well, there could be four. I'm just going to write down all of them, and then we will see what they are. Okay, so let's start off with case A. This case is very simple. Okay, let me list all the cases first of all. In case A, as the person pushes on the box slides, the person does not move. That's case A. Then the second case is as the person pushes on the box, it is quite possible that the box does not move but the person slides. Then third thing it can happen is that as the person pushes on the box, it is possible that the box will start tipping by contacting the corner point instead of sliding. Okay, it will tip before it starts sliding. And likewise, the other thing that can also happen is if the person has some dimensions given, the person could also be tipping. So we don't know. Okay, so I'm going to write down all of these cases. So case A, as the person pushes on the box, the box can slide. Okay, box can be on the verge of sliding, and the person stays put. Okay, which essentially means that if I look at the friction force between the block and the ground, or the box and the ground, this friction force is actually equal to mu bg times nbg. This is because motion is impending between the block and the ground, but that is not the case between the person and the ground. Mu person ground should be less than mu pg times npg. Okay, so motion impends between B and G. Here, motion does not impend between the person and the ground, and the important thing is there is no tipping taking place. Okay, so I'm just going to call it as 1, 2, and then 3. In this case, no tipping. Okay, this is case A. Then I go to case B. It is possible that as I apply the force, or as the person applies the force on the box will tip before it slides. Okay, so as person pushes on the box will be on the verge of tipping. Okay, by using the contact point C as the fulcrum. Okay, using the contact point C as a fulcrum. Okay, and the person stays put. Okay, this is an important important situation. Okay, now when there is no tipping motion taking place, here is the conclusion that you can gain from it. Okay, and there is no tipping motion taking place. The location of the normal force. So usually when you draw the free body diagram and so on, where do you draw the normal force? You draw it passing through the center of mass. That is wrong. In most cases, the location of the normal force is not known. Okay, so you don't necessarily draw it as a line passing vertically through the center of mass. You draw it at an unknown location. Okay, so in case of a sliding motion, you know that the normal force location is not known to us between the box and the ground. Okay, so I'm just going to write this down. So location of the normal force is not known, okay, when there is no tipping motion. But if there is tipping motion, here is what is going to happen. The equations that will be satisfied are the following. See, there is no motion impending, so this will not be impending. Okay, that's the first thing. The second thing is there is no motion impending between the person. Should be less than mu person g times npg tipping possible, which tells me that the location of the normal force is now known. And where do you think this is going to be? This normal force is now going to be at the corner point of contact. Okay, so that's something that I want to see. So this will be the location, and I'm going to mark this down. So this will be the location labeled as C on the box. Okay, I just want to go up and complete these before I go up. So both of these say that motion does not impend between the person on the ground and the person on the block, but the tipping motion is possible. That is the situation that is shown here. So that is what I'm saying by saying that, okay, hey, if there is tipping taking place, then I know that at this particular contact point, everything is going to be situated based upon this contact point here. Okay, the entire box is going to use that as a fulcrum and then start tipping. But everything else is still not sliding, right? Only when you have sliding, you have impending motion taking place. Okay, all right. Then I have the third case. What is the third case? So case C, I guess. In case C, it is possible that as the person pushes on the box, the box will stay put. And the person might start sliding. Person on verge of sliding. Okay, which means that in this case I'm going to have f mu bg to be less than mu bg times nbg, f mu pg to be equal to mu pg times npg, and location of npg is not known. Okay, this is the third case. And the last case, case D, which is not a case that we are going to be considering. The person can tip. Okay, as a person pushes on the box stays at rest and the person tips. Okay, this is a case that we will not consider because we don't know the dimensions of the person. You can consider tipping only when you know the dimensions. Okay, so we shall not consider case D, since we do not know the dimensions of the person. Alright, so we have some heavy lifting to do in this problem, as you can see. Okay, how to solve this problem? So first of all, we need to understand what it means to tip versus slide. Okay, so try to understand tip versus slide. That is the first thing that we're going to be doing. Okay, now what I'm going to say is the following. Okay, I'm going to just grab the box, just hang on for a minute or so, or maybe a second or so. I'm just going to grab this box, I'm going to copy that, and I'm going to paste it down here. Okay, I'm going to draw this 2 times, so one time here, and then 1 time right here. Okay, so, and this is all on the flat ground, as you can see. Okay, in the first situation, I'm applying a force P, which is very, very close to the ground. Okay, so the force P, and this height is some height h1. Okay, in the next figure, I'm applying the force P at a height much further away from ground. Okay, and I'm going to write down the following. This is some height h2. Okay, and of course this is your contact point C, as you know from before. Okay, so this is the figure. So this is figure 1. This is figure 2. In figure 1, what is happening? The height at which the person pushes on the box is very close to the ground. Okay, the height, I need to write this in the normal color, the height at which the force P is applied is very small. Okay, in figure 2, this height at which the person is pushing on the box is very large. I'm just going to, being lazy, just going to copy all of that. Apologies. Okay, so this is the situation. Now this is very large. Okay, in this situation it was very small. In the previous case it was very small. Now this is going to be very large. What is the situation here? If the height h is very small, so this height h1, let me call it as h1. Okay, so h1 is a small value, and then in this case h2 is a large value. Okay, if the height h1 applied is a very small value, then it means that the box has a greater chance of sliding than tipping. Okay, so which means that if h is small, box has a greater chance of sliding first, right, rather than tipping. Tipping means rotating about a certain point. Okay, and if the height h is large, then the box will probably tip first. Okay, rather than sliding. Which implies that there is a minimum height. Okay, so this implies there is a minimum height h minimum at which the box has an equal chance of tipping and sliding. of tipping and sliding at the same time. Okay. So what does that mean? Okay. So for our problem, okay, look back at our problem. Okay, so we go back to our problem, and I see that, okay, hey, there is a certain height. The person pushes the box at a height of 0.75 meters from the ground. Okay, so that's the height h. I'm going to call this as the height h. Okay, so the person pushes the box in our problem. Person pushes on the box at a height of h is equal to 0.75 meters from the ground. So if we can show that h is less than h minimum, then we can kind of avoid tipping motion. Okay, so then more chances of sliding is more. Okay, if h is greater than h minimum, chances of tipping is more. And if h is equal to h minimum, then tips and slides at the contact point C. Right? If it is tipping, then there's going to be only one point of contact between the box and the ground, and which means the sliding is going to take place at the same point as well. So what is our aim then? Our aim is to calculate this h minimum. Okay, so obtain this h minimum at which the box is on the verge of tipping and sliding at the same time, and sliding at the contact point. Okay, which means that at h is equal to h minimum, I have the following equations. F mu bg is equal to mu bg times nbg. Okay, and the location of the nbg is known to be at the point C. Okay, C is the contact point. This is precisely what we're going to be doing. Okay, then I'm going to just draw the free body diagram of the box and the person pushing on the box. Okay, so let me do that. All right, so this is our aim. If I can calculate h minimum and then compare it to the height given, I can then get rid of one of my cases. Okay, so that's exactly what I'm going to be doing. I'll grab one of these figures. Okay, I'm going to capture this figure here, copy that and bring it down here. Okay, so I'm going to draw the free body diagram of the box at the minimum height, and our label will take care of that. Okay, so this is going to be the ground, as you can see here. I don't need to draw the ground as such, but that's good enough for me. Okay, this height is going to be h minimum now. Okay, so this is h minimum. I don't know this height, and what are the things that I do know? I know the weight of the box, which is acting vertically down. Okay, so this is the center of mass of the box. Okay, the geometric center of the box, and then so this is the weight of the box, which is acting vertically down, that is equal to 500 newtons. The location of the normal force is known because this is the contact point C, right? Which means that the location of the normal force is known to me, and so this is going to be N BG, and then the direction of the friction force opposite to the force applied, and so that location is also known to me, F mu BG. And so what are the equations that I have? F mu BG is mu BG times NBG, and this was given to us as I think, if I remember right, 0.3. So this is 0.3 NBG. Then if I sum forces in the y direction, set them equal to 0. What are my forces? NBG minus W of the box is 0, so that NBG is 500. Since this is 500, I can then find out, okay, what is F mu BG. Okay, so F mu BG is going to be 0.3 times 500, so that's 0.3 times 500. So F mu BG is going to be 150 newtons, as you can see. Okay, then I sum forces in the x direction. What are the forces? There are only two forces here, right? The force P, the force F mu BG. So I'm just going to do that. So P minus F mu BG is equal to 0, which implies that P is equal to 150 newtons as well. Now comes an important thing. In this situation, I know the total width of the box is given to me as 1 meter. If you go back to the main problem, right, look at that distance is given to you as 1 meter here. Okay, so which means that I can make use of that distance. I'm going to make use of that here. Watch this. So this total distance is 1 meter, which means that this distance here is going to be half a meter, right? So I'm just going to put that as dotted lines. And so that is going to be 0.5 meters, 0.5 meters, and then I'm going to sum moments about the point C. Okay, look at that. So I'm going to sum moments about the point C and then set that equal to 0. What are going to be the moments about point C? Force P times the distance of H minimum clockwise. WB times the distance of 0.5 meters counterclockwise. And that's about it. Okay, so this is going to be WB times 0.5 minus P times H minimum is equal to 0, which means that H minimum is WB, which was 500 times 0.5, and all of this is divided by 150. Okay, so if I do this, I get this to be approximately 1.6 meters. 1.6 meters. Now I go and check and see. In our problem, H was given to us as 0.75 meters. So H is less than H minimum, which means that tipping can be discarded. Okay, so in our problem, I'm just going to write this down. Okay, so in our problem, H applied was 0.75 meters, which implies that H is less than H minimum, which was 1.6 meters. Okay, if I do the comparison. Okay, so this implies that we know for sure that the box does not tip as the person pushes. Okay, which means that, this was the second case that we had written down. If I go back up here, the third case, case C, which means that case C can be neglected. I guess not. Case C was a different case. Sorry, case B can be neglected. Okay, so which means that the tipping motion is now discarded and thrown out of the window. Okay, so this implies that case B can be discarded. Okay, so tipping is not going to take place in our situation. Okay, that is the main thing. So we know that there is no tipping possible. The box does not tip at the height at which we are applying this force of 0.75 meters. Okay, So which means that I'm going to go to the first case, the case A of the box. Okay, so then select case A and see if the friction inequality is satisfied. Inequality of this case is satisfied after solving. Okay, so then case A, what are the equations that we have for case A? Okay, in this situation we're going to have F mu Bg is equal to mu Bg times NBg. The inequality is F mu Pg is less than mu Pg times NPg. And the third thing, no tipping, which means that the location of NBg is not known. Location of NBg is not known. This is very important. Okay, if you have tipping, then you know the location of the normal force. If you don't have tipping, you don't know the location of the normal force. Okay, so I'm going to draw the free body diagram. Okay, so free body diagram of the box. Now look at this. I'm just going to bring this free body diagram and then start doing some adjustments on that. Okay, so watch this. I'm going to clean this up a little bit. Okay, so here is the free body diagram. Now first of all, this is no longer h minimum. Okay, this height is known to me as 0.75. Then the second thing is I'm going to get rid of all of these guys because they're not very useful for me at this point in time. The other thing is that this force is now no longer here. It is acting somewhere here. And of course, this is acting anyway tangential to the ground, so it does not matter where you think it is acting. And so here is what I'm trying to say. I'm trying to say that there is now a distance here between the line of the weight of the body and this normal force, and I'm going to call that distance as x. Okay, so here x is an unknown distance. Okay, so that's what I'm saying. But then there are some things that I know in this problem. I know that since I'm assuming F mu Bg to be sliding, it's on the verge of sliding, I can say that this is mu Bg times NBg. So let me start doing some calculations and so on. Okay, so I'm going to sum forces up in the y direction. That's the easiest way to start, right? I'm going to get NBg is equal to the weight WB. So NBg is equal to 500 newtons. Then this implies that F mu Bg, which was 0.3 times NBg, this is now going to be 150 newtons. Sum of forces in the x direction gives me P is equal to 150 newtons. This gives me that force P minus F mu Bg is equal to 0, so that P is equal to 150 newtons. And it's not necessary to find that distance x, but just in case if you want, here is what you can do. Now I can, this point I had called as the point C, right? So I can call this point as the point D. Okay, so this point here, I'm going to call as the point D. I can sum moments about the point D and set that equal to 0. And here is what I'll end up getting. If I do the summation of moments, it's WB times X, P times H. Okay, this is no longer H minimum, this is just H. Okay, this is the height that is actually applied. Okay, so this is going to be WB times X minus P times H is equal to 0. So that X is equal to 150 times H, which was 0.75, divided by the weight, which was 500 newtons. And after doing the calculations, this comes out to be 0.225 meters. Okay, so which tells me that x is 0.225 meters. This is something that you may watch out for in a problem and ask you, okay, hey, if it is not tipping, or if it is not tipping and it's only sliding, where is the location of the normal force? Okay, so this tells us that NBG is located at 0.225 meters from center of the box. Okay, all right, so moment of reckoning. Okay, we need to test and see if our answer is correct. To see if our answer of P is equal to 150 newtons is correct, we need to check and see if F mu Pg is less than mu Pg times NPG. Which means I have to draw the free body diagram of the person. Okay, so here is what I'm going to do. Grab that person from up here. It's the first time we are handling this person with care. Okay, I'm going to copy that. Okay, and bring that person down here. Okay, so now I draw the free body diagram of the person. Okay, as I'm doing that, very quickly draw the person here. Of course, I don't need the ground and so on. Okay, now the person is pushing on the box to the right, which means that the box is going to exert an equal and opposite force back on the person. Okay, so this is the force by which the person had pushed on the box. There is going to be an equal and opposite force back on the person. Okay, so this is the equal and opposite to force P exerted by the person on the box. Okay, then what else do I have? I have the weight of the person, which is acting vertically down, okay, somewhere through the center of gravity of this person. Let me grab this and put that here. Okay, so this is the weight of the person, which was 750 newtons. Then I'm going to have the normal force. Now in this case, I don't know where the normal force is acting on the person, but the dimensions are not given to me, so it does not really matter to me. Friction force is now going to be acting this way. Okay, so this is going to be F mu Pg. Sum of forces and so on will be what is going to be done here. Okay, if I sum forces in the y direction and set that equal to 0, NPG is equal to WP is equal to 750 newtons, which implies that and I can sum forces in the horizontal direction. Forces in the x direction is equal to 0. Sum of all these forces gives me F mu Pg is equal to the force P applied, which is 150 newtons. Now check. Mu Pg times NPG is going to be 0.4 times 750. Right, and that's going to be 300 newtons. Okay, and then we know F mu Pg is equal to 150 newtons, which means that I have to compare. Okay, and if I do the comparison, we end up getting F mu Pg is less than mu Pg times NPG, which means that our assumption is correct. The inequality is satisfied. Okay, so which means that the minimum force with which the person pushes on the box for motion to impend is 150 newtons. Okay, so this is the minimum force. All right, so I want to just briefly jot down a couple of points as well here. I want to draw three figures where I show sliding versus tipping and tipping and sliding together. Okay, so let me do that very quickly. So just a brief summary of tipping and sliding. Okay, this is the important concept that we have been looking at in this particular problem. Okay, I want to draw three figures. Okay, so in the first figure, I want to draw a box, of course, and I want to copy this and paste it. Okay, all right, beautiful. So copy that, and I want to do this 3 times. Not sure what I'm trying to do here, but so this is 1. Let's see, this is 1, then this is 2, and this is going to be 3. And all right. So here is what we got. So figure 1, figure 2, figure 3. Okay, in figure 1 there is only sliding, no tipping. Okay, so in figure 1 I'm going to say that H is less than H minimum. Okay, so sliding and no tipping, which means that in that particular case, you will see that the force applied will be somewhere here. This is the force P. Okay, this is the height H. Okay, what are the things that you'll see? You'll typically see that let me just bring it down here. Okay, this is sliding and no tipping. The things that you'll see is that the weight of the body which will be acting vertically down. Okay, and then the location of the normal force will not be known in this case. Okay, if you're on the verge of sliding, the location will not be known. So I'm going to be drawing it at some point here. Okay, and then this is the direction of the friction force. So this is N BG F mu BG. Okay, so and what I'm trying to say is that this is not known to me. This distance here is an unknown distance x, but since I have sliding and tipping, right, this implies that F mu BG is equal to mu BG times NBG. Okay, this is the situation for figure 1. Then I have figure 2, and then I have figure 3. In figure 2, let me draw figure 3 first. Okay, so here is figure 3. In figure 3, look at this. The force applied is at a very high height. Okay, so which means that in this case I'm going to say that this is the force P. The height applied is much larger than the minimum height. Okay, so this is H, and in this case I'm going to say that H is greater than H minimum, which means there is tipping only but no sliding. Okay, which means that the location of the normal force in this case is known to me. Okay, you see that, right? And the friction force is also known to me in this case. I want to just scoot this slightly on this side so that I can draw the friction force. Okay, so the location of the normal force is known to me, and BG, location of the friction force, is of course tangential to the contact surface, F mu BG, and then I have the weight of the body which is acting vertically down. Okay, so in this situation, when I have tipping only but no sliding, I know the location of the normal force. So in this case, F mu BG is less than mu BG times NBG. Location of NBG is known. Okay, then I come to the situation where I have both of them taking place. Okay, which means that now I'm at a critical height, or the minimum height. This is P. Okay, this is now going to be H minimum. Okay, and of course I'm going to have the weight of the box. In this case, now you see that the normal force and friction force are still at the corner point, but I also know that the friction force is related to the normal force. NBG, this is F mu BG. Okay, this is the third situation where it is tipping and sliding. Okay, and if that is the case, F mu BG is equal to mu BG times NBG, and location of NBG is known. Okay, so these are the three things that you would like to see. So here H is equal to H minimum. Okay, so this is the first case where there is only sliding. This is only tipping. Okay, and this case sliding and tipping. Okay, so these are the three things that we have seen in this particular problem, and I hope this problem was very useful to all of you. In this case, a quick recap is that the person is pushing on the box. What is going to happen? What is the minimum force to push the box so as to cause motion to impend? Several cases. One case is box slides, the person stays put. Second case is the box stays put, the person slides. Third case is the box is going to tip by using the contact point C as the fulcrum, and the person stays put. The fourth case, which we don't consider in this problem because the dimension of the person is not given to us, is that the person himself or herself or themselves can tip and the box will stay put. Okay, we go through the different rigmarole of finding these minimum height H, as I have shown here. Okay, once you find a minimum height and then find out that the height that which we are applying the force is larger than this, then tipping can be neglected. So we go to the next case where we have sliding, which is case A. Go through the equations and then find out if the inequality is satisfied. Once you see the inequality satisfied, end of the story. And this is a brief summary of tipping versus sliding motion here. When you have only sliding motion, you don't know the location of the normal force. Okay, so here location of normal force is not known. Is not known. In the other case, the location of normal force is known, but the friction relationship is not known. Only when you have only tipping. When you have both sliding and tipping, you know the location of the normal force, and you also know that there is a relationship between the friction and the normal forces. All right. I hope all of you are staying safe. Take care of yourselves. This is an excellent problem. Please try to go back and look at it again. Okay. Thank you very much and take care. Bye-bye.